Okay, so welcome back. So we have a little bit to tidy up with complex eigenvalues and eigenvectors before we move on to chapter 6. So last thing I wanted to say about them is the following. So let's do one more quick example. So let's say let A be say 0, -1, 1, 0. All right. Now, if I want to find eigenvalues and eigenvectors of this thing, what do I do? So first I write out the characteristic polynomial. Of course, this is a 2 by 2, so there's this shortcut I mentioned. So I could think about this as being lambda squared minus trace of A lambda plus determinant of A. What's the trace of this matrix? 0 plus 0, so that's 0 here. So this is lambda squared minus 0 lambda, so I'm not even going to write that term, plus determinant of A, so this is 0 times 0 minus 1 times minus 1, so that is minus minus 1, or plus 1, so this is lambda squared plus 1. Okay. What are the roots of this characteristic polynomial? So the roots are lambda equals plus minus I. And so those are my eigenvalues. Okay. Those are my eigenvalues. All right. So, how do I find eigenvectors? You might have a complaint from last time, which is I just immediately threw in complex numbers into my vectors and just didn't mention anything about them. So at the very beginning of all of this stuff, the very beginning of the semester, I mentioned that everything we're going to be doing in this course, basically, with very little modification, could be done if I just replaced all my reals. So when I mentioned first in chapter 4, when we were talking about scalars, when we were talking about generic vector spaces, instead of using R, the reals, for my scalars, I could have used complex numbers instead, and actually it doesn't really change anything about what's going on. In terms of algebraically what we're doing, very little needs to be modified at all for all this stuff to carry through. And so actually it turns out what we're doing is perfectly fine, but you'll see how it all works out here. So for a second, for the rest of this course, other than in this section, for the rest of this course, whenever you have a vector or a matrix written, it is assumed that all of the entries are real. The only time when that is not assumed, unless I say otherwise, is exactly where we're in this section of dealing with complex eigenvalues and eigenvectors. So here's my eigenvalues. Let's find eigenvectors. So let's look at A minus I times the identity, right? So A minus little I times I. Let's look at that. So if I look at this, what do I get? I get minus I minus 1 and 1 minus I. Right? So then I want to look at the equation A minus little I times some vector V is equal to the 0 vector. Right? This is how I find my eigenvectors. So looking at this, I have the matrix equation minus I times minus 1, minus I minus 1, 1, minus I times a vector V, which I'm given entries V1, V2, is equal to 0, 0. Right? And so if I write this out, I would get minus I times V1 minus V2 is equal to 0. And V1 minus I V2 is equal to 0. So for 2 by 2s, if you've gotten used to how this works, you'll see, we did an example of this last time, but you'll see that when we do this, we only have to actually use one of these. That's how it's going to work out for these 2 by 2s. And so, for instance, I could use the second one. So using the second one, this tells me that V1 is equal to I V2. And so I actually get a free choice here. And so if I choose, say, v2 to be 1, then v1 is I. And so an eigenvector associated to this eigenvalue, if I'm calling my eigenvalue lambda 1 I, then eigenvector associated to it, v1, is from this is I1. Right? Okay. All right. Let's check that this is the case. All right. How would we check that something is an eigenvector for some specific eigenvalue? Well, I would actually do the multiplication to check this, to see that this actually works. So looking here, what I should expect is that A times V1 be equal to I times V1. Well, let's just check here. What is AV1? AV1 is my matrix minus I, minus 1, 1, minus I, times V1, which is I1. So let's see what this is. So if I multiply this out, I get minus I times I, which is minus I squared, which is minus minus 1, so that's 1, plus minus 1 times 1. So that's 1 plus minus 1. So what would I get there? I would get 0. Okay. Wait, that doesn't... I'm skeptical. Oh. This... I use this matrix. So I use this matrix. So what I would be checking is that this thing is equal to 0, which is another way of checking it. So what I have written here is A minus lambda 1 I times V, which should be 0. That's another way of checking it. Sure, we'll go ahead and do it this way. This is not what I wrote here. If I wanted to check this, the matrix I would have used obviously is this one. It's A here, not the other one. But anyway, we can check this way. There's nothing wrong with checking this way either. So let's go ahead and finish this then. So this would be 1 times I, so that's I, plus minus I, so that's also 0. So yes, that also works. That's maybe that's not as fun because we actually found this directly from this equation, so it's not surprising at all. We're just checking our algebra here. But if you actually check A times V, so if I multiply A times V, so I1, what do I get? I get, so 0 times I is 0 plus minus 1, so that's, I get minus 1. Right? And then in the second slot, I get 1 times I plus 0 times 1, so I get I. Okay. Is that the correct thing I should get? So this is A times V1, and that should give me I times V1. Well, here's V1. What's I times V1? So I times V1, if I treat it just like a scalar, right, I would have I times I1. I times I is I squared, which is minus 1, and I times 1 is I. So indeed, yes, this is, here's lambda 1 times V1. So this is an eigenvector in exactly that sense. Okay. All right. Yeah, so Yakta, when I have the bar written over it, that's the vector V1. That's the first eigenvector associated to the first eigenvalue. The V1 is the component of V here that I'm finding. Yeah. So I know it's a little confusing. But anyway, so the way that The way that this works now, so I've found one eigenpair. I have found I and the vector I1. This is my first eigenpair. Now I want to find the other one, of course, so I want to do the same thing for the other eigenvalue. I'm going to do this fully, but then I'm going to show you why you don't actually have to do this. And some of you might have already guessed it. So let's look at the other eigenvalues. So let's look at a minus lambda 2I. So that would be a plus little I times I. That's what I'm looking at. So the matrix I get in question is I minus 1, 1, I. Okay. All right. So, looking at this thing, I want to look at a plus I times v is equal to 0. I want to look at this matrix equation. So I minus 1, 1 I times v1, v2 is equal to 0, 0. Okay. And so, writing this out again, this would be I v1 minus v2 is equal to 0. And similarly, this would be v1 plus I v2 is equal to 0. Okay. I'm going to use the second equation again just because that's what I used in the first one, even though maybe you don't think it's as easy. So v1 is equal to minus I v2. Again, the free choice here, I choose v1, or I choose v2 to be 1, and so in that case I get eigenvector that I'm calling v2. That would be, so if v2 is chosen to be 1, then v1 is minus I. And so I get an eigenpair that is minus I, and then my eigenvector is minus I times, or sorry, minus I in the first slot and 1 in the second slot. What do you notice between this and what I have written in the previous example? You notice anything? So here's my eigenpair from the first eigenvalue. Here's my eigenpair for the second eigenvalue. You notice any pattern here? So this might require me to refresh your memory when it comes to complex numbers. Yeah, it's the conjugate. So the idea here is that there's a big fact. If lambda v is a complex eigenpair for A, matrix A has real entries. Okay. Then lambda bar v bar is also a complex eigenpair for A. And so, since these complex eigenvalues always come in conjugate pairs, finding the eigenvectors is easy once you've found one of them. So once you've found one of the eigenvectors, you can get the other just by conjugating. What does it mean to conjugate? So recall, so if z is a complex number, so if z is a plus ib, the conjugate of z is a minus ib. Okay. Another thing we might as well take our time to remember. Another thing is the real part of a complex number z. So the real part of a complex number z, if z is a plus ib, the real part is a. What is the imaginary part? The imaginary part is b. And I want you to notice, this is a thing that always trips up students, both of these are real numbers. So, just to repeat it, the imaginary part of a complex number is real. That's actually the entire point, right? It is, all you're doing here is you're picking out the real numbers that define that complex number z. Okay, so both the real and imaginary parts are real numbers. You can apply the real and imaginary parts to a vector. So, for instance, if you had the real part of a vector, say, that had two components, z1 and z2, what is that? That is the vector that consists of the real part of z1 and the real part of z2. And so the real part of a vector that has complex entries is a vector that has nothing but real entries. What is the conjugate of a vector of complex numbers? It's the conjugate of every element. Okay, so that's a good question. So it's the same thing. If you have a vector, I'll do it over here since I've run out of room. So if you have a vector v that is complex, when you conjugate it, it is conjugate of v1 and the complex conjugate of v2. So you are doing the complex conjugate in every slot. Okay. Right? And that's what's needed to do this. And so if we actually check what we did here, let's go back to our first thing. So we took this. If we wanted to get the other eigenpair for the conjugate, we would conjugate this. This is just I, so its complex conjugate is minus I. And we look at this vector, and we conjugate I, which becomes minus I. The conjugate of 1 is just 1, right? Because there is no imaginary part. So this is a complex number. It is 1 plus 0i. So then the complex conjugate is 1 minus 0i, but that's still just 1, right? So the complex conjugate of a real number is just the same thing, right? So another thing I should say, if a is real, then a bar is equal to a. Right? So complex conjugating a real number does nothing. Okay, that's how you can tell what's going on in this pattern, because it couldn't be anything else, right? So when you look at this, comparing these two things, it couldn't be multiplication by minus 1 here, because even though you've switched to be minus I, have minus I here, the 1 remains unchanged, right? So that's how you know it's complex conjugation and you're not multiplying by 1 or something like that. Okay, so this is good that we went over this, because this is actually needed for what we do next. Okay, and so what do we notice? What do we notice about matrices A? And you can restrict your attention to 2 by 2s, although this is going to be true in general. But what we know about matrices A with complex eigenvalues? What is something that immediately you notice? So let's recall our example. So let's go back to our example. We have a matrix A. And our matrix was 0, minus 1, 1, 0. We saw that it had eigenpairs I1 and minus I, minus I1. I'm going to do something just to show you an algebra trick here. So the algebra trick that I want to show you is these eigenvectors are defined up to scalar multiplication, but the scalars we're allowed now are bigger, right? We're actually allowed scalar multiplication by complex numbers. So another eigenpair for this would be I minus 1I. That works. Why does this work? Well, this is scalar multiplication. I times I1. So I took my eigenvector from the first eigenpair and I multiplied by the scalar I. Right? Okay. Yeah, so someone's asking about multiplying a vector by a real scalar versus multiplying it by a complex one. So we're going to see exactly right now what is going on with rotation here and what having a complex eigenvalue means. The first thing you note is, what if you tried to diagonalize this? All right, so what if you try to diagonalize your matrix A? Well, remember how the process of diagonalization works, right? You want to try to form this thing, but when you form this thing, what would you get here? You would get P would be, in this case, I'm gonna do it. This is my first. This is my second. So your P would be this thing here, right? Times D. Your eigenvalues were I and minus I. Like what is this? Right? What is this? You can't do this. This is not, and included in our diagonalization was not any description or discussion of complex stuff showing up here. In fact, this is no good. All right, we can't do this. Okay. So it's not diagonalizable, right? Automatically. Because the P and the D in question must have real entries. So when we diagonalize, our P and D must have real entries. Now, there's something to be said here. Later on, when you're doing questions of more, when you're doing more high-powered linear algebra, you can in fact diagonalize in this way. It would be called diagonalization over the complex numbers. So if you're willing for your matrices to have complex entries, then of course you can diagonalize it, and the way that you would diagonalize it is exactly like this. Okay, so that involves the concept of diagonalization over some specific field, so say C instead of the reals. But for us, when we say diagonalization, we're only talking about over the reals. So I'm not even going to make that distinction. For us, when we say diagonalization, P and D have to have only real entries, just like every other matrix and vector we ever deal with in this course has only real entries. So I don't want to go down that rabbit hole too much. But the point is that I can't diagonalize this, okay? But we can get close. So we can kind of diagonalize A. So what does this kind of diagonalize involve? It's the following theorem. So there's a theorem. It's very nice. It's about complex eigenvalues. So what does this theorem say? So let A be a 2 by 2 matrix with real entries. So okay, with complex eigenvalues. Well, if it's got 1, then it's got 2. They come in a conjugate pair. We'll say the complex eigenvalue in question is lambda equals A minus BI. Okay? That's what the textbook says. You can do this perfectly well picking the A plus BI when it doesn't matter. So B, here is not 0. If it were 0, then we'd just be dealing with a real entry matrix. Or, sorry, a real eigenvalue matrix. Okay? So if this has complex eigenvalue lambda and an associated eigenvector v, right, which typically is going to have complex entries In fact, not typically. It is guaranteed to have complex entries. So this is an associated eigenvector V, which has entries in the complex plane. Okay, then A can be written as PC P inverse. Okay, where P is the matrix whose columns are the real part of the eigenvector V, the imaginary part of the eigenvector V, okay, in that order, and C is the matrix A minus B, B, A. Okay. What does this matrix do? What does this matrix C do? Okay. Well, this matrix C is a rotation. Recall your standard matrix for a rotation. Right. How is this a rotation? Well, to see this, so this is the theorem. This is the content of the theorem. The fact that this is a rotation is a separate matter. To see that this is a hidden rotation, C is the matrix A minus B, B, A. And this can be written as R times A over R minus B over R, B over R, A over R. That might seem like a very strange algebra trick to do, but I can think about this as R, 0, 0, R, right? And this second matrix here is very suspicious. Why is this second matrix very suspicious? If I go to the plane and I write in a picture a triangle here, where here is R, here is the point AB, right? Here's B, of course, here is A, and here is an angle, say, phi. Well, what is this? These are just sines and cosines, right? Remember SOHCAHTOA. So this is cosine of phi minus sine phi, sine phi, cosine phi. What is this? This is definitely a rotation, right? So this is rotation, counterclockwise rotation through an angle of phi. So this is rotation. And then this is a scaling, right? So this is a scaling. And so hidden in a matrix C that is of this form is a rotation. So this is the hidden rotation. So now that you've seen this, right? So now that you've seen this, going back to this theorem, what does this say? While I can't diagonalize A, I can write out that A is similar to a matrix C, where hidden in this matrix C, the C is of a very particular form, the A and B coming from the eigenvalue itself, the real and imaginary parts of the eigenvalue itself. So this matrix C that A is similar to is a matrix that contains a hidden rotation in it. And so multiplying by a matrix that has complex eigenvalues is a rotation, basically. So that's how complex eigenvalues lead to a rotation matrix. Question, how did I get that scaling matrix? Well, can I do this? I factor an R here that's non-zero, right? R is some non-zero thing. Do you agree that R times A over R is A, R times minus B over R is minus B, R times B over R is B, and R times A over R is A? Right? I'm factoring out an R that doesn't exist and then putting it in the denominator, right? I can always do this trick. Okay, so that's where the R matrix comes from. Because multiplying, of course, by a scalar R is the same thing as multiplying by the matrix R times the identity. In the homework, do we have to solve for P inverse for the diagonalization? No, you just have to find P. You don't have to find P inverse. Okay. All right. So this is the last thing I wanted to say about matrices with complex eigenvalues. So can't diagonalize them like this, but hey, you get this really, really nice fact that instead of having a diagonal matrix here, you get this matrix that's a rotation. So multiplication by a matrix that has complex eigenvalues is a rotation in some sense. Okay, so that is that. And that finishes our chapter 5 discussion. And so we come to chapter 6, which takes us back to abstract. Well, I mean, actually, at first we do all this stuff in Rn, but a lot of our treatment of it is going to be reminiscent of what we did in chapter 4. So inner product, or I should just say the inner product, but inner products, orthogonality. This is the first thing that we're going to talk about. Okay, and so quick definition. You've seen this before, but maybe you haven't seen it exactly in arbitrary dimensions. So my definition, let's say that I have two vectors u and v in Rn. All right. So the notation I'm always going to use when I write these is I have a vector u that has entries u1, u2, and so on all the way to un. Similarly, a vector v has entries v1, v2, all the way to vn. Okay. The inner product or dot product or scalar product, you will hear all of these. Inner product is kind of the best thing to say here. Dot product is fine because this is a specific inner product, but when you're doing more high-powered stuff, the main thing that's nice about this is that it's in fact an inner product. So there's other more general examples of things that are inner products, but this one is the best one. And so what is this thing? This is u dotted with v. And you'll see immediately why it's called the scalar product, because of course we started with two vectors u and v. We dot them together. What do we get? We get the linear combination of, well, not a linear combination. It's literally just adding the product of the entries component-wise, right? So some people like writing u as a row vector, if you like, and then multiplying this by the column vector for v. Of course, this is u1, v1 plus u2, v2, and so on, the way to un, vn. Okay. That's the dot product. All right, so of course you've seen the dot product in R2 and in R3. This is something that was very important in Calc 3. It turns out that the importance of this can't really be overstated. This is basically the most important thing ever. The reason it's the most important thing ever is that it is the thing that gives length. Okay, so Length has no meaning without this thing. This is the thing that defines length. Your ability to compute a distance is dependent on this thing. So this is the thing that tells you how to find the distance between 2 points in space. All right, and without it, it is impossible to do that in the normal sense. Okay, so we'll see in a second how that is. So first, a couple of examples. Or maybe I should say a couple of properties, and then we'll do like a quick couple of examples. We don't have to do many because all of you are familiar with at least the basics of the dot product. So let U, V, and W be in Rn. Okay, let C be a scalar. All right, so C is just an R. So then a couple of things. So one, the dot product is commutative. So it doesn't matter in what order you do the dot product. Okay. The dot product has a distributive property that if you add two vectors and dot their sum with a third vector, this is the same thing as adding the dot products U dot W plus V dot W. Okay, third thing, if you scalar multiply a vector and then dot it with another vector, that's the same thing as scalar multiplying the end result dot product, which of course is the same thing as scalar multiplying in the other slot. Okay, and then the last thing is positive definiteness. That is that a vector dotted with itself is always greater than or equal to 0, and a vector dotted with itself is 0 if and only if the vector itself is the 0 vector. So that's the only way you can get 0 when you dot a vector with itself. Okay. Now, of course, we can actually combine iterations of these properties together to get you, you can do this. You don't have to just do this with two vectors here. You could sum any number of vectors you want, and dot. You could also include linear combinations, right? So instead of just having sums of vectors, you could have linear combinations of vectors, and you dot them, and you get everything you want. So combining 2 and 3 here, you get that dot products behave very nicely with respect to linear combinations. Okay. Now, quick example. So let's let U be, say, 2 minus 5 minus 1, and let V be the vector, we'll say 3, 2 minus 3. All right, what's U dot V? Well, it's 2 times 3 plus minus 5 times 2 plus minus 1 times minus 3. So this is 6 minus 10 plus 3. So this is 9 minus 10, so this is minus 1. Now you might be tempted to ask, like, what is the number that you get out of this mean? And you might have a hard time finding some geometric meaning in the number itself for two given vectors, unless that number is a particularly special number. So you already know what I'm going to say here, right? If you dot two vectors together and that's 0, that tells you something special geometrically. Apart from that, dotting a vector with itself gives you nice info. But in general, dotting a vector with some other vector and getting something that's not 0, it can be hard to figure out what it is that's going on geometrically there from that alone. And so here's another definition that is very important. The length or norm, okay, of a vector u in Rn is defined to be the length of u, which is the square root of u dotted with itself, which is the square root of u1 squared plus u2 squared, and so on to un squared. A couple of things I want to note. You might say, wait, why are you calling this a definition? I already know what the distance formula is for 2 points in arbitrary, R in space. So why are you calling this the definition when I already have a definition for it? So we're going to treat this as the definition because even if we didn't, this is hiding in that, right? This is how you define normally the length of a vector. But this hidden in this is how you define the distance formula in space. And the distance formula in space corresponds to what? How do you get the distance formula? So if you've never seen this before, then you can have a look at it. I'm not going to draw it up. I'm not going to draw it in 3 space. Drawing it up in the plane is really easy, so I encourage you to do that. This is just the Pythagorean theorem. So the Pythagorean theorem is where the distance formula comes from. So if you draw in the vectors in question in the plane, and you look at the distance formula or the formula for length of a vector in the plane, this is just a Pythagorean theorem. And so doing this in Rn is just the Pythagorean theorem in Rn, basically. You can draw a right triangle where this makes sense, okay, in some plane. That's the motivation for why this works the way that it does. And of course, we want the Pythagorean theorem to be true when we're talking about Euclidean space. So this is what we want. So it turns out that however you came across this formula, note, hiding in the background is the dot product. Okay. In fact, from this definition, note, we have an identity. Okay, that comes directly out of this definition. So the length of a vector is the square root of that vector dotted with itself. So the dot product determines the length in this way. Another way of writing this, right? This is true if and only if a vector dotted with itself is actually the same thing as the length of that vector squared. Okay. So looking back at this fourth property up here, when you dot a vector with itself, you always get something that's greater than or equal to 0. And the only time this thing is actually equal to 0 is when you're dealing with a 0 vector, which has 0 length. So now we know, intuitively another reason for that being true is that, oh, well, dotting a vector with itself, that's the length of the vector squared. So clearly the length of a vector squared, that can only be 0 when the length of the vector itself is 0. The only vector that's true for is the 0 vector. Right? Okay. Another thing that I get immediately is, here's another property. So here's another fact you might recall from the case of R3. What happens if I take the length of a scaled vector? What is this? Well, if I actually try to compute this, of course, this would be c u1 squared plus c u2 squared, and so on. c un squared. So in each term, I get a c squared, right? Well, let's just do it real quick. So this is c squared u1 squared plus c squared u2 squared, and so on. So this is c squared un squared. What is this? I can factor out the c squared. What's left is u1 squared plus and so on un squared. So this is absolute value of c times what's left is square root of u1 squared plus and so on un squared. That's just the length of u. So scaling vector scales the length by absolute value of your scale factor. Right? So just rewriting that. So scaling the length of a vector scales, or I should say scaling a vector, scales its length by the absolute value of the scale factor. This is something you knew from R3. Okay. All right, so that's another nice fact. Okay. Now, we can use this, of course, to define distance, right? So now that we have length, we can define distance. So here's definition. So distance between 2 points. Okay. And so let u and v be vectors in Rn. We know, since it's been beaten into your heads by now many, many times, that vectors and points are the same thing, really. So vectors in Rn are the same thing as points in Rn, right? That those vectors point to from the origin. And so these are points in the space Rn. I can talk about the distance between them, right? So then the distance between u and v is the following. So what's the distance between u and v? This is the distance between u and v. This is the length of u minus v. So, just to recap, the dot product gives us length of a vector, and length of a vector in this way gives us the distance between 2 points. And so, tracing through that string of ideas, the dot product gives you length, okay, or distance. Okay. All right. So we are tying together all these geometric quantities here. Now, recall in R2, if u dot v is equal to 0, what does this mean? In fact, I'm not going to include the word if here. What if I have u dot v is equal to 0 in R2? What does that mean about u and v? Well, this means, so it means something geometric. All right, so recall your calculus 3 knowledge. They're perpendicular, right? That's exactly. All right. So one of them is a zero vector. That's not true. So you can, what I want you to do is come up with u and v such that neither of them are the zero vector, but their dot product is 0. Okay, so you can definitely do that. So let u be 1, 0, let v be 0, 1, right? So let u be I and let v be j in R2, and then I dot j is 0. Even though neither of them is 0. So this means that u and v are perpendicular. Okay. Now that's very, very easy to see in the plane. But the notion of being perpendicular, of course, that is still a geometric configuration that is possible in space. It's possible in R3. So it's possible like that. It might be a little bit hard for you to see. But the notion of being perpendicular is true in space. It's also true in R4, R5, R6. But because the pictures are harder to draw and because thinking about it is a little bit more complicated, typically the word that is used for being perpendicular in higher dimensions is orthogonal. Okay, and so that's what we'll say. In fact, our definition is that two vectors, so u and v in Rn are said to be orthogonal if u dot v is equal to 0. Now, of course, orthogonal is not a property a vector can have by itself. So when I say orthogonal, we mean to each other. So orthogonal only makes sense relatively, right? It only makes sense relative to some other object. Okay, it doesn't make sense on its own. You can't say this vector I have here, vector w, it's orthogonal. The question is orthogonal to what? Right, orthogonal to some other vector, orthogonal to a plane. You have to specify. Okay, and so orthogonal is just higher dimensional perpendicularity. Okay. All right. In fact, tying this together, we have the following fact. So we have the theorem. What is this theorem? I'm not going to name it first. I'm just going to say two vectors, u and v, are orthogonal if and only if the length of u plus v squared is equal to the length of u squared plus the length of v squared. What is this theorem? It has a name. It's about 2,400 years old or 2,500 years old, maybe actually a little bit older than that. Yeah, this is just the Pythagorean theorem, right? So this is the Pythagorean theorem. Okay, and I mean this is true in Rn here. This is not just in R2, but this is this is true in Rn. So those of you mentioning the triangle inequality, we'll talk about the triangle inequality. I at least might actually throw it into one of the exercises here. I'm sure there's some exercise in one of these sections that deals with it. But this specifically tells you that, yeah, if you form the triangle u, v, and u plus v, that triangle is, if that triangle is a right triangle, then you get this. If not, well, then you get the law of cosines is the best you can do. And so law of cosine, you'd have some extra term here. But when u and v are orthogonal, you get this. In fact, we actually showed this in another form earlier in this class using what was the vector form of the law of cosines. Okay. All right, so I think that's pretty much it. I'm about to define orthogonal complements, and that's about it. And then we're gonna. So this seems like some kind of toss away thing. I just defined orthogonality here on the previous page, but this is going to be the central focus, right? So maybe I'll write that. So orthogonality is the central focus of this entire chapter. Okay. So vectors being perpendicular to each other, or orthogonal to each other, is an extremely important geometric configuration because it has really, really, really nice properties. So the easiest way for me to explain this to you is think about R3, think about the standard basis vectors in R3. Why is it so nice to deal with and compute with the standard basis vectors in R3? Well, they're orthogonal, and they're also something called orthonormal because they're unit vectors. They're orthogonal, they're unit vectors, they are in the nicest form possible because of that. Okay, and we'll see exactly what I mean by that when I define the notion of an orthogonal set, which I will do next time. Okay, so next time I'll start out defining orthogonal complement, talk about orthogonal sets on Wednesday, and we'll proceed from there. So chapter 6 won't take us too long at all. In fact, I hope to have finished chapter 6 entirely by not this Friday, but next Friday-ish. Okay, is when I will have finished this entirely. Anyway, So I will see you all on Wednesday. Remember, I have office hours on Wednesday. I assigned homework in MATLAB Project 1. If you didn't see the announcement, have a look at that. So bring any questions you might have about those things on Wednesday for office hours. But anyway, I will see you all then.